Hello, Professor Zoran, can you hear us?
I am back. I had to switch off my computer and switch it on, so it took some time to boot the computer. I'm back. I will start my presentation. Perhaps I'm not going to use.
Just as you can open it.
Yeah, let me open it.
Dear ladies and gentlemen, we're glad to welcome you to the session dedicated to dynamical astronomy, and we are glad to have as a chairs of this session Professor Srđan Samurović. Srđan, you are welcome to take over session and start it.
Thank you, Angelika. Do you hear me?
Yes.
Okay, I don't see my video opened.
We will not now turn off your video because Professor Zoran should share.
Okay, no problem. So we may start now, I think.
Let me try to share the screen.
Thank you.
Can you see now at least something?
We can see it. We are not moving anything. You're
Okay, thank you. Well, thanks for the invitation, and I apologize for this technical problem, which was for unknown reasons, but okay, now it seems that it is okay. Well, I will speak about the problem with which I am, let's say, dealing for already a couple of years. Some time ago, with my late colleague Andrea Milani, I proposed a new method to compute the frequencies of asteroids, the secular frequencies of asteroids, which can then help in finding positions of secular resonances, in particular the secular resonances in the asteroid belt, in a much more precise way than it was possible before. Let me introduce, for those who are not familiar with the concepts, in celestial mechanics, the notion of secular resonance. In the same time, I apologize to those who are familiar with the things that I'm going to say, quite well-known things. Nevertheless, secular resonances can be defined in different ways, and one definition, which is sort of working definition and a little bit mathematical, not so much physics in it, says that secular resonances are singularities in the phase space of orbital elements, where linear combinations of frequencies of the longitudes of perihelia and nodes of the perturbed asteroids and perturbing planets bodies tend to zero. Well, what does it mean? This means that in the equations of motion, when you integrate them over the time, you get in the solution, you get a typical term in the solution which looks like this comparatively simple equation, and I will just tell you what is what in this equation. Now, this is the amplitude, which at this particular context is not so much so important. Here is the trigonometric part of the perturbation, which contains the linear combination of the angles of the longitudes of perihelia and longitudes of nodes of both or all the bodies in the dynamical model. And H is a vector of integers, which actually represent the factors or multipliers of the angles, together giving a linear combination of the angles multiplied with the sum integers. Now, when you, of course, the angles change with time, and when you integrate over time, you get the divisor, which contains the same vector of multipliers, but this time in combination with the frequencies. The frequencies are actually the rates of the longitude of perihelion and longitude of node. They are usually labeled with letters, lowercase letters G and S. Sometimes the longitude of the node rate is also, you can find in the literature, lowercase f. But let's use G and S. And if this combination of the rates multiplied with the vector of integers actually tends to zero, then it is clear that you will end up with the singularity. The load combinations of these multipliers are constrained by the so-called D'Alembert rules. There are usually people quote 3 rules, but let me just mention that, for example, one of the rules is that the sum of these of all the components of the vector H must be equal to 0, that the sum of the components which multiply the longitude of nodes must be even, and so on. So if such a linear combination tends to 0, we are in the presence of the resonance. And there are, of course, the resonances are divided with respect to the number of frequencies involved, a number of bodies involved, and so on. And the most important and the most powerful resonances are obviously the linear resonances, which involve combinations with multipliers 1, 1 of the asteroid, for example, or perturbed body in general, and Jupiter, and or the G of asteroid and the one of Saturn, and as well as the rate of the longitude of node or frequency of the longitude of node and that of Saturn. So these are well-known linear resonances. Of course, the linear resonances exist with all other bodies in the planetary system, but these 3 are the most important, because of course also the Jupiter and Saturn are the most massive perturbers. If the number of bodies and number of frequencies involved in the linear combination is higher than 2, then we are in we speak about the nonlinear resonances. Well, they are nonlinear more or less because they are in the development of the perturbing function, which is then more or less mapped in the equations of motion. These resonances they correspond to the terms in this development which are of degree of higher degree. That's why we call them nonlinear. Of course, it is well known that the rate of the longitude of perihelion of Jupiter is something like 4.26 arc seconds per year, and the period is 300 something, little bit in excess of 300,000 years. And the other 2 values which are commonly known and which come from some of the theories. I think these particular values are coming from the well-known long stop 1b integration of all the planets for 100 million years, which was done a long time ago by Milani et al. Now I have to, okay. Well, back in 1990s, so it's 30 years ago, Andrea Milani and myself published a paper in which for the first time we mapped the positions of the resonances and more or less of all the resonances which were present in the theory of motion of asteroids up to degree 4 in eccentricity in inclination in the first order with respect to perturbing mass, and up to degree 2 in the second order. These resonances involved only the frequencies due to Jupiter and or perturbations due to Jupiter and Saturn, and it was analytical theory, which means that the frequencies G and S could be computed from explicit analytic expressions. G0 is the value which comes from the linear theory, well known from the times of Lagrange, while this nonlinear addition, the term is quite complicated in practice, but of course I'm not going to show all the equations here. Once you compute G and S on the, let's say, rectangular regular grid in the phase space of so-called proper elements, I will say in a few moments what are the proper elements. Then when you have the Then you map the set of the coordinates in this plane directly to the values of corresponding frequencies. And then it is easy using some graphical tool to plot the so-called contour lines, contour lines which correspond to some reasonable small value of the linear combination of frequencies, or what we call also the divisors. By the way, I forgot to say that these small, when divisor small tends to 0 and we have a resonance, that's the reason why maybe you have heard that people in celestial mechanics very often talk about the problem of small divisors. So that's the reason for the problem of small divisors. And all these small divisors, if they are small enough, they give rise to the libration of the critical angle and to all kinds of resonant phenomena. So this was essentially the first time back in 1990 that these resonances were mapped by means of the analytical theory. Now, why we are at all interested in knowing exact positions of secular resonances? Well, this is important for several reasons. For example, of course, then you can be sure that some asteroid is either inside or close to the resonant strip, and then you can analyze its dynamics, having in mind that it is probably vibrating in one of the critical angles, or in the critical angle, or these nearby resonance. Then resonances are affecting the computation of orbital or proper elements of asteroids, which are used as parameters for classification of asteroids into families, which means that if the families are crossed by some resonance, the members of the family will interact with the resonances, and this may essentially reshape the asteroid family as we see it in a given projection on this or that orbital elements plane. Most often we are looking in the plane semi-major axis inclination. Then the secular resonances influence the transport of objects inside or out of the asteroid belt, like for example in the region close to the Earth, so that they can become potentially hazardous objects and so on. So it's a good idea to know where they can come from. So these are some of the reasons. There are many more and so on, but I'm not going to go further into detail in this respect. Of course, because this is an important issue, there are many papers, many people actually tried to determine exact positions of the secular resonances, and there is a list of some older and some newer papers in which this kind of problem was addressed. In particular, there are methods to determine the positions of the secular resonances, which we can consider as a so-called direct methods. This is the method, for example, of computing the frequencies from some kind of analytical theory, like it was done by Milani and myself, as I said, some 30 years ago. And it was a similar method was used, for example, by Yoshikawa even earlier, but Yoshikawa was using a much simpler analytical theory than ourselves, and also much simpler dynamical model. Speaking about the indirect methods, these are not really methods of determining the position of the resonance in the sense that you are looking for a resonance, but instead you are looking for the resonant asteroids. Well, how do you know that the resonant is asteroid if you do not know whether the resonance is there or not? Well, there are some indirect indicators that that the motion of some asteroids is affected by the resonances, and some of these methods are quite simple. Like, for example, I will just mention the method by Novakovic and Tsirvoulis, who actually took the frequency of the perturbing body. In their case, it were the Ceres and Vesta. And knowing this frequency, they were looking for the asteroids which have a frequency within some narrow range around the frequency of the perturbing body, and so on. So there are different ways to handle the problem of essentially not knowing where is the resonance, but identifying the resonant asteroids nevertheless. Still, I have shown you the results of the determination of the position of the secular resonance by means of the analytical theory, 30 years old. However, the analytical theories, of course, suffer from a well-known drawback that that they must be truncated. The expansion of the perturbing function and of the equations of motions must be truncated in some degree of the terms which can be reasonably handled within one such kind of theory, and therefore you necessarily introduce some error in the computations of your of the motion of the asteroid and of the frequencies of the longitudes. That is also in the positions of the resonances. And this error, of course, is more and more severe as you go to the higher and higher values of eccentricities and inclinations. Since nowadays we have a lot of objects in the orbits which have, we know a lot of objects with orbits which have very high inclinations and very high eccentricities, then the analytical theory is becoming increasingly inaccurate. Therefore, we more or less posed to ourselves a goal to improve the accuracy of the positions of secular resonances by trying to combine two approaches, two ideas. One is that we are again still using the direct method using the interpolation on the regular grid in the space of proper elements to compute the positions of the resonances, or to be able to draw contour lines by interpolating in between the nodes on the grid. And but using for the computation of the frequencies the best available so-called synthetic theory for computation of secular frequencies, but the problem is that synthetic theory is completely numerical. And everything which is essentially computed in the synthetic theory is based on the numerical integration, which lasts several millions of years. So in this period of time, the initial position, even if you start from the node on the grid, this initial position will change in a nonlinear way, and you cannot assign the final value of the frequency to the initial condition. So that's the problem, and we had to find a way to overcome this problem, and that's exactly what we have done with this particular new method which I was mentioning. Again, let me emphasize that in analytical theory, secular frequencies are explicit functions of the proper elements. Now it is time to say what are the proper elements. So the proper orbital elements are obtained from the oscillating ones by removal of the short and long periodic perturbations, which means that they are nearly constant in time, and more technically saying they are quasi-integrals of the equations of motion. In the synthetic theories, frequencies are instead computed, as I just explained, via numerical integration, so they do not explicitly correspond to any specific point in the phase space, including the nodes of the grid. So what we can do? Now, the solution was introduced already in the paper of Milani from 1994, where he was applying a kind of rudimentary version of the method to the problem of finding the frequencies and resonances in the region of Trojans. It was, let's say, the method proved to be quite successful, and later on, we more or less developed a more sophisticated version, but based on the same ideas. and produced this new method, which I'm going to present you now. The idea is essentially, as I said, quite simple. The idea that since we do not know the frequencies for the nodes, let's compute the polynomials in the term of the suitable Cartesian analogues of proper elements, with coefficients computed by the method of least squares from the catalog of asteroid proper elements and frequencies. So just take all the asteroids wherever they are, compute by least squares the coefficients of a polynomial, and you have an explicit expression from which you can then compute the frequencies for any point or any set of coordinates in the phase space. So the idea is essentially quite simple, but nevertheless it requires a lot of preparatory work to be applied appropriately. So for example, of course, there is a trivial task of choosing the catalog which you are going to use for the fit, and the appropriate dynamical model, which more or less depends on where you are looking in the asteroid belt, in the inner belt, where you have to use also the inner planets, or in the outer belt, where you can more or less end up with using simplified dynamical model with only 4 perturbing planets and so on. Then the asteroid belt is a quite complex dynamical region with dynamics which changes depending on where you are in the belt, which means that in order to apply the fitting, you have to try to split the entire asteroid belt into dynamical zones within which the dynamics is uniform enough to justify the more or less fitting of the model to all the asteroids which reside in a given zone. This is done in such a way that we have more or less defined 9 different dynamical zones within the belt, and that these zones are, the boundaries of these zones are more or less places where we have a strong mean motion resonances. Then you have to remove the asteroids from which can be found in the catalog, asteroids which have inaccurate frequencies for very different reasons. And if you want to have a good fit, good accuracy of the fit, of course you have to first get rid of those guys which can spoil your result. Now the little bit of techniques of mathematics, which is quite simple again. Instead of usual Keplerian variables, it is more convenient to fit the polynomial in the Cartesian variables, and then we just introduced for the sake of convenience the Cartesian variables which are normalized in such a way that regardless of the dynamical zone, of the definition of the dynamical zone, these variables are between 0 and 1. Then next we have to more or less, and these are simple equations which do this, which perform this task of transforming the variables. Then we have to define the monomials, which we will more or less incorporate in our polynomial, and these are also formed quite simply with the only remark that all the monomials in the polynomial are of even power, because this is a kind of course, they are even in a basic variable, which is in this case eccentricity, for example, and or inclination, or better to say sinus of proper inclination. Now, 0-degree monomials are connected only with the semi-major axis, while the others of the even degree are connected with the eccentricity and inclination. In degree 2, we have up to 12 monomials. In degree 4, we have up to 24. And in the degree 6, then this is the highest degree which we were using up to now, we have up to 40 monomials. And sometimes when the dynamics was indeed complicated and not easy to resolve in terms of the motion resonances, we used also the couple of additional higher degree monomials in semi-major axis only, but only in a couple of zones. So there is the table with the list of all the monomials, and as you can see, they are very easily formed. Once you form these monomials, you have everything, and you use the catalog of proper elements and frequencies. Then you have all the ingredients for the usual or the common method of least squares to compute the coefficients of the polynomial, and these coefficients are given with this couple of vectors of in terms of for the frequency G and for the frequency S. G is a covariance matrix, F is the transpose of the design matrix, and G and S are vectors of the frequencies obtained from the catalog. That is, these are real frequencies computed for the real asteroids. Of course, you can just solve these equations and get the coefficients, which means that you ended up with the explicit expression in the form of the polynomial, which depends on the coordinates of the points in the phase space of proper elements. Now, of course, in this kind of space, you just define some sort of a grid. Typically, you have a two-dimensional grid with a third proper element fixed to some reasonable value. I can explain what does it mean reasonable, but let's keep it for the moment. And and in this way, you have two coordinates. Two coordinates which change from one node of the grid to another, and the third one which is fixed for all the nodes, which gives you essentially a surface of section in the three-dimensional space. And introducing these coordinates in the polynomial which you have previously computed, then it is easy to get straightforward the frequencies which are associated with the nodes of the grid. Then as I said, by interpolating in between the nodes of the grid, you compute the corresponding contour lines, and you have contour lines corresponding to the small values of the divisors of the resonant combinations of frequencies, and then you can plot the positions of the resonances in this particular plane. Of course, all this computation requires that you very carefully control the accuracy of the computation, which can change from one zone to another. And this is done, of course, by computing simple standard deviations of the coefficients of the polynomial. Then you can compute signal-to-noise ratio, just ratio of the coefficient with the standard deviation. But the most important accuracy control are essentially the post-fit residuals. Namely, having now the polynomial expression, you can introduce also the coordinates of all the asteroids, or the real asteroids in the same expression, and having their frequencies computed already by means of the synthetic theory and the frequencies computed from the fit, then you can judge from these residuals, you can judge on the accuracy of your fit and of the computation of resonances on the grid. So that's what we are doing. Now let me show you some results. The results, of course, I cannot show you the results for all 9 zones which I was mentioning, all zones in the asteroid belt. So I've selected just one zone in which I think we have quite interesting results which show you what do we do with this knowledge of where are the resonances, what is the information which we can extract from this particular information. So let me show you the results on the zone which is called zone of Hungary asteroids. Hungary asteroids is a zone of the asteroid, or the group of the asteroids which are isolated from the rest of the main belt. They are closer to the sun with respect to the main belt, and residing on quite high inclinations and on the moderate to low eccentricities. Now here in the plot you have something like 6,485 asteroids which belong to the Hungaria group. But the Hungaria family are red points, which means that inside of the group we have a collisional family, which shows all the characteristics of the asteroid families, like so-called V-shape and so on. So already in the paper of Milani et al. From 2010, we identified essentially all the important resonances, secular resonances, and the mean motion resonances, which are not plotted in this particular graph, but they are also there. And these resonances are either linear resonances like this one. Here we see just one contour line, the other two are outside of the plot. Here is another one, here we see at least two. And we have also some non-linear resonances which we are going to see in more detail now. So the linear resonances bound the region, but non-linear cross the region. So you can see here a simplified plot where some of these resonances which are crossing the non-linear resonances which are crossing the region are shown together with objects inside of the Hungaria group, which have the large errors of eccentricity and inclination, which is on the other hand the indicator that these objects might be resonant. And of course, if you see that you have object which have a large error of the proper eccentricity, and you see that its position in the phase space coincide with the position of the resonance, it's not difficult to conclude that the resonance, that these objects are resonant, and that resonance affect the computation of proper elements, deteriorating their accuracy. Now for the zone, we of course estimated the goodness of the fit. And as you can see here, all these values are given in arc seconds per year. When you take all the asteroids, regardless of their individual errors, or residuals, then you get the fit which is good, but in particular not that bright, that very good in terms of frequency G. But if you discard just a couple of objects, which are, as we term them, pathological cases, which have very, very large residuals, then you already improve the accuracy of the fit in such a way that it is difficult to say that it is even necessary to improve it further. 1/10 of arc second per year is extremely good accuracy. Of course, these pathological cases are defined as cases which have residuals which are in excess of the 10 sigma. If you discard a little bit more of the objects which have 3 sigma residuals larger than inside than 3 sigma, then you get essentially almost perfect fit. Now, of course, once you know that there are some pathological cases and cases of deteriorated accuracy, you would like to know what is the reason. And of course, with the red points are the points which show the positions of the 3 sigma outliers, while the green points are these 2 objects which are, or 6 objects in this case. This is for frequency G and this is for frequency S, that are essentially discarded in the fit, in the final fit. And one is easy to see that here this is eccentricity, Here we have objects with a very small eccentricity, which are subject typically to a problem which is called cycle slip. I have no time to explain what is this, but there is a well-known problem for the very low eccentricity objects. But here we have a little bit more complicated situation. Here is one nonlinear secular resonance crossing the region, and you see that a good number of the affected asteroids are within this resonance strip, but not all. Perhaps this one, there is another resonance, maybe not yet identified, which affects the rest of the objects and so on. Here is the mean motion resonance, so we know why and so on. Okay, so good fit, and we have a pretty good idea what is the reason for the problems. Now, once we have this, what we can learn from this kind of information, where is the resonance, and that we know the position of the resonance well. Well, here is one such an example. There, in the paper by Warner et al. Published in 2009.
We are sorry, 5 minutes more.
5 minutes, okay, thank you. I will try to wrap up. We have the case in which they shown that inside of Hungary group, the family seems to be very compact, above 1.92 astronomical units, but a little bit spread in terms of the same, but below 1.92 astronomical units. They consider the possibility that these are satellite families, deciding that after all, it doesn't seem to be very probable. Then they made a couple of experiments just by integrating the orbits which started from here, and due to the non-gravitational Yarkovsky effect, they migrated towards the sun, and they have shown that a number of objects from the group which they integrated shown a slight increase of the inclination, but a little bit smaller number of objects have shown the larger decrease towards the larger change towards the smaller inclinations. They suggested that this is due to the interaction with secular resonances, but they didn't know which ones. They suggested that they proposed a number of resonances which involved not only Jupiter and Saturn, but also other perturbing bodies, other major planets, and even showing that in this particular resonance, the objects, when they are crossing it, they librate and change the direction of the circulation before and after the crossing of the resonance. So these are more or less very strong indications that this object really passed through that resonance. They also claim that this other resonance of order 6 might be important and so on. And what this new tool, what I have done is to find the positions of all the resonances which they suggested may be responsible for their problem, and essentially showing, and also adding some more resonances which they didn't consider, and finding that indeed the resonances are just located in the right place. So you see here is that this part of the phase space where this change takes place, and this coincides with all these resonances, both of order 4 and order 6. So once the asteroid enters the resonance by migrating due to the Yarkovsky effect, it enters the resonance, it slides along the resonance until it reaches the opposite side, when it is released from the resonance and continues with the constant inclination. So my results corroborate the proposed scenario of Warner et al., but my results also show that there is no single resonance, which, as they assumed, but there is a multiplet of all kinds of different resonances which affect the motion of the asteroids in the Hungary region, so that we can be sure that this is the reason for observed spread of objects in the region and not the existence of another family. And this is my last couple of slides, or slides which are devoted to the.
1 minute.
Yeah. Okay, let me try. There was a doubt that maybe here there is another family, because here we have less dense concentration of objects than here, so that this can be perhaps the second family. This one is very big and very compact. This might be a little bit more loose, but still it seems that it is separated from the rest of the group. But I have shown that there is a resonance of degree 6 of a previously unknown or identified, which exactly goes there and probably makes this apparent this apparent boundary in between the two regions. So, in my opinion, this probably is not a separate family. Last slide, showing just all kinds of zoom of the resonances in the space of the frequencies themselves, and the asteroid belt, from which you can very easily see which resonances affect the asteroids in which part of the belt and which do not, and so on. So, okay, thank you very much.
Thank you, Professor Zoran. We do not have time for any question or comments, maybe to leave it for after the session.
For a chat, or for a chat.
Yes, for the chat. Srijan, are you there? Hello, Srijan.
Hello. Hello.
Can you please lead the session?
Angelica, do you hear me now?
Yes, could you lead the session? Thank
Yes,
you.
yes, thanks. I can start now. Okay. So we now proceed with our next speaker. This is Dr. Bojan Novakovic from the Department of Astronomy, Faculty of Mathematics from Belgrade, and he will present his talk, Water Content in Compositionally Primitive Asteroid Families, Insights from the Main Belt Comets. Please, Dr. Novakovic.
Okay, thank you. Can you hear me?
Yes, we can hear you.
Good. Hello, everyone. Thank you, organizers, for inviting me. Okay, let me try to share my screen. Okay, can you see it?
Yes, but put it please in presentation. Yes, okay, now it's in presentation mode. Thank you.
Okay, good. So my today talk will be about possible presence of water in small solar system objects, but located relatively close to the sun, what let's say we are calling inner solar system. And in my case, this will be everything we care about the water in the solar system. Well, there are two main motivations. There are diverse reasons, but two main motivations are basically related to formation of the planetary systems and delivery of the water to the systems or the planets in habitable zones on one side. And recently it starts to be very attractive to investigate possibility to use the water ice as a fuel for transportation through the solar system. So these two general reasons and many others are basically cause the diverse investigations whether there is a water in solar system and how much water we can expect. Okay, on this slide, I just remind you what is the part of the system that I'm talking about. So basically, we have here 4 inner planets from Mercury to Mars, also Jupiter, and we have between Mars and Jupiter this concentration of asteroids, which is called asteroid belt. So I will primarily focus on possibility to find the water ice in asteroids located between Mars and Jupiter orbit. Of course, we have ice on planets, not just on the Earth. We know that there is a water on Mars, also on the Moon, and there is a lot of water in the outer solar systems. For example, icy satellites of Jupiter, Oort cloud, trans-Neptunian regions all of this not shown in this plot. But what about the evidence that we have so far about the water in the asteroid belt in smaller objects? So let me give not systematic, but let's say hopefully useful review on this. I will start with the largest asteroid, which is Ceres, the largest object in the asteroid belt. And recently, it was a few years ago, it was visited by Dawn spacecraft and investigated in very details. And this analysis reveals that this is actually an ocean world consisting of containing a lot of salty water. Roughly speaking, if I remember the number correctly, about 30% of the volume of the Ceres is basically water. And as a curiosity, it is even geologically active in a form of cryovolcanism. So what is basically mechanisms very similar to what we know as a volcano on the Earth, but instead of ejecting lavas, in cryovolcanism, you have water ejected from the inside to the surface, and as the surface of the Ceres is very cold, it is immediately frozen and stay as a small mountain. So Ceres is definitely water world, and it is located in the asteroid belt. But this is the largest object there, almost 1,000 kilometers in diameter. What about other asteroids? About 10 years ago, spectroscopic observations suggested that which is located around 3 astronomical units from the sun, and it is a relatively large asteroid, nothing like Ceres, but still are more than 100 kilometers in diameter. And the analysis suggests that it has some water or water ice on its surface. Later on, there was similar evidence for a couple of other asteroids, suggesting that water may be present on some asteroids in the asteroid belt. There are, however, some doubts about that, because the interpretation of this shape of the spectra is not unique and could be explained even without assuming the presence of the water. But having in mind or taking into account all the aspects that we know about these objects, this alternative explanation seems much less likely. So probably we have also spectroscopic evidence that Themis and a couple of other asteroids has water on its surface. But these are again objects which are on the order of 100 kilometers in diameter. Do we have any evidence for even smaller objects? Well, actually, yes. And this is how we are coming to so-called active asteroids, or more specifically, main belt comets. So what are active asteroids? Well, as you probably many of you know, when we see some kind of tail of a small object, we are referring to the comet. However, let's say roughly in the last 2 decades, asteroid-like objects were discovered to exhibit comet-like activity. What basically means that they are moving on the orbits which are typical for asteroids. They have orbits in the asteroid belt, but they exhibit a kind of a tail showing that they are active in some way. There are a variety of explanations, or at least 6 explanations, what can cause this activity in asteroids. However, one of these explanations, which seems only plausible explanation for a significant subpopulation of active asteroids, so-called main belt comets, in which activity is caused by the sublimation of volatile ice or water ice. How we know that? Because all other mechanisms are typically should not be typically correlated with the distance from the sun, or should not last for a very long time. So main belt comets are active for a long time, and typically when they are close to the sun. what is strong evidence that this is sublimation of volatile materials. Just briefly looking where they are located in the solar system. So this x-axis is basically proxy for heliocentric distance. So this is asteroid belt between 2 and 3.5 astronomical units. And you can see that blue dots are main belt comets, while the black dots are the rest of active asteroids identified. And you see that basically all blue dots are located a little bit further away from the sun, no one inside 2.5 astronomical units, which may be also related to the fact that they have some ice. But generally, they are located everywhere in this part. So if this object contains actually water ice, it might be widespread across the asteroid belt. But what is the problem here? The problem is actually how so close to the sun ice can survive in asteroids. We expect that it's too hot at this heliocentric distance for ice to survive. However, deeper analysis and the thermal models are developed to study this situation. And what is obvious is that ice exposed at the surface very rapidly, very quickly.
Bojan? Bojan, we lost you. We lost you. Please do not play presentation in, just open it, scroll down through the slides, not play in presentation mode. It seems that something is wrong.
Okay, can you hear me now?
Yes, just please click on it, open it, and do not play in full screen mode.
Okay, I can do that, but this should not be a big issue. Maybe I just move away from my wireless point, so maybe the reason.
Okay.
Okay, just a second.
All is fine.
So can you hear my slide?
Yes, we can see you perfectly. Thank you.
Okay, so can I continue now?
Yes, of course, you're welcome.
Okay, thank you. So these models shows that ice can survive buried inside the asteroids just a few meters below the surface, if the mean temperature is not above about 145 Kelvin. So further analysis shows that for many asteroids,
Bojan, we can't hear you. Hello, Bojan.
Okay, seems that
Are you there, Bojan?
Yes, I am. Sorry.
Okay,
it seems that my internet connection is not very stable. So models shows that I will skip a little bit these slides now. Model shows that actually buried ice can survive over the edge of the solar system if it is buried just a few meters below the surface. But then we have another question. Okay, we need somehow to bring this ice from below the surface on the surface in order to sublimate. There is, however, relatively simple and natural mechanisms to explain that. These are impacts by small meter-sized asteroids. They impact the larger asteroids, so kilometer-sized asteroids, quite often or often enough to basically expose ice to the surface. Because when we have an impact, if the top layer is basically dry, but we have some layer containing the water below, the impact can excavate this material and bring this ice to the surface, and we can have sublimation or activity, which we connect with main belt comets. There is another problem, however. Over the time, all these impacts will basically excavate all accessible ice below a few meters from the surface, meaning that at some point, even the top layer of a few meters will be completely dry, and the mechanism would not work. Still, of course, we can have more deeply buried ice, but this ice is not accessible to small impactors. However, what is noted over the years is that many active asteroids are associated to so-called asteroid families. Zoran talked a little bit, I don't know if he mentioned, the asteroid families are basically a group of asteroids formed in the collision, in the disruption of larger asteroids. So all asteroids from one family originate from the single body. And many of active asteroids are linked to such a families. And actually typically to families younger than about 10 million years. Why this is important in the context that we are explaining? Well, if we have deeply buried ice, the way to bring it close to the surface is to destroy completely the body. And this is how we form the families. Of course, such impacts are more rare. You should not expect very often to have such impacts, but they are happening on the billion years of time scale. They are happening quite often. So what is the general mechanism then? So we have ice on the surface, which sublimates very quickly. Then the small impactors bring the ice, which is shallow ice, few meters buried on the surface, and we can have sublimation later on due to this process. Finally, once this ice is spent, disruption of the body can bring deeply buried ice on the surface and reset the whole process. This is how actually we can have still some ice present on the surfaces of asteroids even today, more than 4 billion years after the formation of the solar system. To better understand the relation between families and active asteroids or main belt comets, we performed a systematic investigation to identify all families, or to have a global picture about the links between main belt comets and asteroid families. And our analysis has shown that 10 out of 12 main belt comets known at that time, and 5 out of 7 other active asteroids belongs to known on candidate families. However, what is very important here is that all main belt comets are associated to such a families which are composed of primitive taxonomic classification, which is typically linked to presence of volatile materials, which is fully in line that we expect that main belt comets contain some ice. Even a couple of main belt comets which are not associated to any family could be linked to some of these families via dynamical evolution process that can take place in the past. The other active asteroids are linked to the families, but to diverse type of families, not only to primitive families. And there are basically several families linked to main belt comets, but 3 of them contains the most of main belt comets, and these are Themis and Theobalda families, which both have 4 main belt comets associated to them, and Lixiohua family, which have 2 main MBCs linked to it. To further strengthen the link between primitive families, main belt comets, and water, let me just mention a recently published study that performed spectroscopic analysis of 43 Lixiohua family members. This is one which have 2 main belt comets as members. And spectroscopic properties shows that all these members are consistent with primitive composition, and also confirm that the spectra of two main belt comets is very similar to the spectra of other family members, because we in principle expect that family members have similar composition or almost the same composition. So these data show that actually that's true, and that composition of all members of Lixohua family is actually very similar to two main belt comets. If main belt comets contain water, then most of these members should contain some water. If we look at again the plot which show let's say heliocentric distance of these families, which are shown in gray in this plot, I don't know how clearly you can see it, but what is important is that some of these families, including, for example, Themis family, are located close to these gaps that you can see, so-called Kirkwood gaps, which are associated to mean motion resonances. And these are actually some of them are very effective transport roads from the main belt to the near Earth region, to the vicinity of our planet. So this motivates us to consider, can some near Earth objects actually contain water? This is even more unlikely if we know that we are very close to the sun in this respect. So we studied specifically if asteroids originating in Themis asteroid family could preserve ice all the way towards the near Earth region. And basically we studied dynamical evolution of the trajectory, how it evolved from the Themis family to the near Earth region. But then we take into account what's going on with the temperature on the body during this trip. And what we found, modeling temperature and ice loss, we found that basically majority of ice loss is occurring in the main belt, long before an asteroid reaches the near Earth region. This is because actually the asteroid spend much longer time in the asteroid belt than in the near Earth region. Indeed, in the near Earth region is much hotter, but the objects stay much shorter there, and actually the ice loss is smaller. What is, however, important to preserve some ice is that you have that asteroid have continuously small axis title. That spin axis is more or less all the time orientated as 90 degrees towards orbital plane. Basically keeping, first of all, polar regions safe from ice loss. There are reasons, though we know that asteroids rotates as a planets, but their rotational spin axis is not that stable as in the case of the planets. There are some reasons to believe that that axis can stay relatively close to 0 degrees, basically over the whole this considered period. And okay, on the plot on the right, you have two different angles of the spin axis. For small angle of 25, which is blue, we have a lot of ice close to the surface, just a couple of meters below the surface, while for a larger spin axis, so obliquity spin axis orientation, we closer to the orbital plane, the ice can be preserved, but at larger depth inside the body. So to summarize what I was talking about, we can conclude that water ice is widespread among the primitive asteroid families. We know that, as we saw, that main belt comets are linked to families and exclusively to primitive families. The spectroscopic data also show that they have very similar spectra as the rest of the members, and we, due to the repeated activity and correlated to the distance from the sun, we believe that main belt comets activity is sublimation driven. So they should contain some ice. As they are similar in composition with other family members, the other family members should also contain some ice. But that means that families contains many small asteroids, kilometer-sized asteroids with water inside it. Dynamical evolution of these families can spread out these objects or these size basically everywhere in the asteroid belt, and even as we show in the near Earth region. Thermal models suggest, ice retention models suggest that ice in these objects can survive over the age of the solar system, and under certain conditions, primarily spin axis, appropriate spin axis orientation, icy objects may even arrive and be present in the vicinity of our planet. Thank you. I'll stop here and take any question if you have.
Thank you, Dr. Nakovic. Are there any questions, comments?
I have a question, may?
Yes, please, Dr.
Okay,
Knežević.
you can, Zoran, you can first.
Okay, thank you. Well, Bojane, nice talk, thank you. I have a comment and question. The bad news for you is in a way that in a recently published paper by Milani, Knežević, Spoto, and Paoliki on cratering families, which means that these are families where the parent body is not fragmented, is not disrupted. The Theobalda is considered as one of the cratering families and not the fragmentation ones. So it would be a good idea to look in your identification of the active asteroids in Theobalda in terms of Theobalda not being fragmented.
Well, okay. I mean, Theobalda is some kind of bordering case between cratering and catastrophic. If it is cratering, it was very huge crater on it.
Well, okay. Possibly, yeah. Okay. So you have been looking in that already?
Well, yeah, okay. We were not specifically looking at whether these are cratering or total disruption, because even if we have a cratering, if the crater is deep enough, which is like, let's say 1 kilometer, this is much deeper than what small impactors can access. So this does not prevent the mechanism.
Good, but the fraction of the fragments with respect to the parent body is comparatively low for Theobalda, so it's not clear whether it is a very big crater or not. Okay, anyway, just a suggestion, give a more careful look in that particular case.
Yeah, okay, thank you.
Okay, thank you, Dr. Knežević.
Okay.
Any other questions, comments?
I have one question.
Yes, please.
Do you hear me?
Yes, please.
Yes.
Ivana.
Which is the main mechanism of delivering water to our Earth, in your opinion, Bojan?
Okay, that's a very complex question.
Yes.
I mean, it is probably delivered after the initial formation by small solar system objects and likely asteroids. But it was thought until recently that these have to be these kind of icy objects located further away in the main belt. But recent analysis have shown that even S-type rocky asteroids could be source of Earth water. So it is probably mostly from the main belt, asteroid main belt, but it is not clear which asteroids deliver that exactly.
Okay, thank you for the answer.
I have a question also, if we have time.
Yes, please.
Okay, if active asteroid is a result of a catastrophic disruption of a parent body, so which would brought some inside material to the surface of the fragment, is it reasonable to assume that we should expect significant variations of albedo across the surface of that fragment? And do we have some observational evidence for that?
Oh, well, yeah. I mean, in principle, we know that, for example, recently near-Earth asteroids Ryugu and Bennu were visited by 2 spacecraft, Japanese Hayabusa 2 and US OSIRIS-REx, and they both reveal variations of albedo on the surface of these asteroids. However, observing kilometer-sized active asteroids in the main belt from the Earth or even from the space-based observatories cannot give us such resolution to basically detect variations in albedo.
Maybe with the light curve. I don't know. Maybe it can be connected.
Well, okay, I'm not sure, maybe, but it is generally difficult because they are not so easily to observe. These are
But
very
is
small
is it expected to have significant variations?
Well, okay, depends. I mean, if there is ice present on the surface, definitely we should expect some variations. So how large they would be, I'm not sure really. And it is also a question because the ice exactly on the surface cannot survive for very long. But yes, if we observe directly now the main belt comets, it should be there.
Yes.
But yeah, I'm not sure. But some variations in albedo are definitely expected, but at what level, I'm not sure, and whether it would be reasonable to expect to observe this at the moment. Because even for example, I didn't mention, we believe this is sublimation driven, but there were attempts to detect basically molecules in the coma, but actually the level is too small to detect from current instruments.
Oh, okay, thank you.
Bojan, can you hear me?
Yes.
I would, if you stay in this session, maybe I could give you a 7th explanation for the origin of main belt comets. So just one comment.
Good.
Comment.
Okay, thank you. I think that now we can proceed with our next speaker. We had this 7-minute delay at the beginning, so now we proceed with Dr. Ivana Milic-Žitnik, and her talk is functional relations between time resonance strength, Yarkovsky drift speeds, and eccentricities in motions of resonant asteroids. Ivana, please.
Thank you, Sergey. Just let me to play in full mode presentation. It is okay now. Do you hear me? Excuse me, do you hear me?
Ivana, we can hear you.
Yes, we can hear you.
Okay, thank you.
But we will stop your video because something we cannot see your presentation. Now we can see full presentation.
Okay, you can free to do that. Hello everyone, and thank you for the session for the introduction. I will present a new description of the orbital behavior of resonant asteroids under the influence of the Yarkovsky effect. This is content of my today presentation. First of all, as we know, the long-term dynamics of asteroids is governed by gravitational and non-gravitational forces. The most non-gravitational force is the Yarkovsky effect. The Yarkovsky force is anisotropic emission of thermal radiation due to thermal inertia. This effect changes orbital elements of small bodies, especially their semi-major axes, as the most important gravitational force that acts on small bodies on the other side is mean motion resonances. Mean motion resonance exists or creates on places of our solar system where 2 or 3 celestial bodies have revolution periods that are simply integer ratio of each other, like our Jupiter, Saturn, and some asteroid. The Yarkovsky effect creates principally a secular drift in the semi-major axis asteroids, forcing an asteroid to cross over and mean motion resonances, while the mean motion resonance causes periodic oscillation in the semi-major axis asteroids around its center. As a result of the interaction between the mean motion resonance and the Yarkovsky force, the semi-major axis is modified. Thus, it is very significant to investigate the influence of mean motion resonances of different strands on the asteroid semi-major axis, while the semi-major axis has modification due to the Yarkovsky effect. The siblings of the Yarkovsky effect, named Yarp effect, and also the collisions among the asteroids are bound to introduce uncertainties in asteroids' orbital motion, but averagely and statistically, the calculation in our studies, which will be presented now, are reliable. One our interesting result from 2019 from the last year showed that asteroids with Yarkovsky drift speed less than 7 times 10 to minus 5 astronomical unit per million year move rapidly across mean motion resonances, especially across strong ones. Therefore, we excluded that asteroids from our studies. Now I will present the general equation between lead lag time that resonance asteroids spend in mean motion resonance and between strength of resonances SR and Yarkovsky drift speed with eccentricities, orbital eccentricities of asteroids in the range from 0 to 0.1. In order to investigate that relation and to derive that equation between time that asteroids spend in the mean motion resonances, their strength and Yarkovsky drift speed, we used numerical integrations in public domain Orbit 9 numerical integrator. In this purpose, we used 66,000 test asteroids with orbital motion between 40 and 120 million years, depending on the strength of the resonance and of the value of the Yarkovsky drift speed. We used a numerical method which is described in detail in our papers Milic, Žitnik and Novakovic from 2015 and 2016. In this purpose, we track motion of asteroids across 11 isolated mean motion resonances with Jupiter. We choose Jupiter because this is the largest and the most massive planet in our solar system. Of course, in every orbital motion of test asteroids, we include, as I said before, the Yarkovsky effect as the pure acceleration that induced in average semi-major axis drift speed, which is pre-adopted. We adopted 10 equidistant Yarkovsky drift speed from -4 times to 10 times 10 to -5 to -2 times 10 to -3 astronomical unit per million year. That is reliable values of the Yarkovsky drift speed for main belt asteroids. In this figure, you can see these 11 mean motion resonances between Jupiter and the asteroid. Now in this figure, it was presented, one can see dependence between this time lead lag of that asteroid spent in mean motion resonances as a function of logarithm of strength of resonances, and on the left figure and on the right panel, this figure, you can see dependence of DTR of logarithmic values of the Yarkovsky drift speed. And of course, I have to say again that we presented these results without the slowest Yarkovsky drift speed because of previously mentioned behavior of asteroids with a smaller Yarkovsky drift speed than 7 times to 10 to -5 astronomical unit per million year. And we derived, this is a very new equation which describe these three very important properties of resonant asteroids. On the left side, time that asteroids spent in resonance, mean motion resonances under the influence of the mean motion resonances and Yarkovsky drift speed. And on the right side, you can see strength of resonances and the Yarkovsky drift speed, and we calculated this unknown beta gamma C2 for, and we derived this equation for eccentricities from 0 to 0.1, and for inclination 5 degrees and perihelion and angle of perihelion for 60 degrees. We derived two equations for all 11 mean motion resonances, and for the 6 the strongest mean motion resonances. We see that the statistically are very the same, these two set of parameters. So we derived one memorable short form of our equation. One, you can see this equation, and the equation one is valid for these values of eccentricity, for these values of the Yarkovsky drift speed, and for these written values of strength of resonance. Now we have to move on the second slide, and now I will present my new results from this year. I continue to this very interesting to resolve the very interesting this issue, but now for asteroids with eccentricity from 0.1 to 0.2, and again I used numerical integrations in public domain orbit 9 numerical integrator, and I used the same numerical method, the same mean motion resonances with Jupiter, and of course the same equidistant values in order to compare this new equation for higher eccentricities and for smaller eccentricities of from interval 0 to 0.1. Now let me just tell you something about calculation of moments of entering T1 and exiting T2 from mean motion resonance. On the left figure, we can see T1 moment that asteroids enter into the mean motion resonance. As a T2, we have periodical changes of semi-major axis around this horizontal gray line. This is the center of resonances in this plane, and we have also the time of exiting from the mean motion resonances, and we have here strong resonance because we have, this is 9-4 mean motion resonance between Jupiter and asteroid, and because of that we have very large periodical changes of semi-major axis around its of asteroids around the center of mean motion resonances. And contrary to this situation, on the left, on the right side, we have very weak resonance 17.6 between Jupiter and the asteroid, and we also marked the time of entering and exiting from mean motion resonances. This is the very known our formula of calculation time lead lag in mean motion resonances, because some resonance can speed up or slow down resonance asteroids which cross over them, and this is one can see in my in our papers from 2015 and 2016 very detailed explanation, and from my and also in my paper from 2019 very detailed explanation about this formula. Now we have to move on the next slide. This is results about strength of resonances on smaller and higher eccentricity for 0.1 and 0.2. We have these numbers of these 11 isolated mean motion resonances with Jupiter. The center of resonance, the second column, and then third and fourth column contain strength of resonances that we calculated with the numerical method given by Gallardo from 2006. And we also can see that on higher eccentricities we have, of course, larger strength of resonances. We have the similar situation. I calculated with our numerical method. I don't have time to explain our numerical method about calculation of width of mean motion resonances, but you can also find in my PhD thesis or on in my previous works about that method. And of course, we got logical and expected the result that the width of resonances on higher eccentricities are larger than on smaller lower eccentricities. Of course, I wrote one table about number of asteroids that crossed over 11 resonances, but without close encounters with planets. Why? In these higher eccentricities, we have a complicated situation on larger eccentricities because we have some unstable regions on higher eccentricity in mid-motion resonance. Because of that, we decided to exclude these asteroids which have close approaches to the planets. And also I have one comment. In averagely, we have smaller close encounters in between asteroids and null planets in these two, the weakest resonance 18.7 and 76 with Jupiter. And finally, this is the newest result about dependence of average time delay caused by the resonance on the resonance strength and on the semi-major axis drift speed. Without, again, the slowest Yarkovsky drift speed, we have the similar situation to do with similar results with our previous result between this dependence. And because we have similar situation between these all values, we got similar. I got a similar equation, and we have some changes we got in our memorable form. If you saw that 0.5 and minus 1.0, but now we added this coefficient dr and db, and also we added this third coefficient because, as I said, of this unstable regions in mid-motion resonances on higher eccentricities. And because of that, we now have two equations which described a situation for the strongest for mid-motion resonance and for the other, the weakest 7 mid-motion resonances. Obviously, two sets of coefficients are different. Coefficients are different in sign because of different relation for two cases of the weakest and the strongest resonances. Again, we derived
Ivana, 5 minutes.
Okay, thank you, Sujan. Again, we derived the differential equation of the first order from the equation 2, as we did the same thing as we did the same thing in my PhD thesis. If one want to see that deriving and that differential equation, you can see only my PhD thesis. And after deriving this equation by unknown coefficients, these 3 unknown coefficients, we derived this differential equation, and we calculated 3 sigma errors for our time lead lag in mid-motion resonances under the influence of the Yarkovsky effect. The first figure, the first part of the first figure, this is the second part, you can see dependence between Yarkovsky drift speed and this DTR time for all 11 mid-motion resonances. And you can see these blue values are from equation 2 that we got from using equation 2, and these red values are from our raw values of DTR, our values that we got from the numerical integrations from the orbit 9. And you can see, one can see that DTR are very good, follow changes. This equation 2 very good, follow the changes of DTR, and for all resonances and for all Yarkovsky drift speed. The second one result is the same result, but now in the different plane. This is the dependence of DTR on logarithm of strength of resonances in all mid-motion resonances for the largest 9 Yarkovsky drift speeds between, again, equation 2 and numerical integrations. And we again, of course, that is a logical and expected result. We again got that equation 2 very good follow. We did 3 sigma errors. These vertical lines are 3 sigma errors of DTR, very good follow. This all changes of this DTR in all mean motion resonances and with all Yarkovsky drift speed. Now we can I can say something about conclusions and further work regarding this very interesting issue. We presented a new description. I will just read these conclusions. We presented a new description of the orbital behavior of resonant asteroids under the influence of the Yarkovsky effect for eccentricity in the range from 0 to 0.2. We derived and established equation 1 that enables easy and fast calculation of the average time that an asteroid spends in a two-body mean motion resonance with known resonance strength, with the Yarkovsky drift speed in this interval, and with an asteroid orbital eccentricity in the range from 0 to 0.1. We derived and established the very similar, of course, equation 2 that again enables easy and fast calculation of the average time, but now we have, of course, the different interval of resonance strength and the same interval of the Yarkovsky drift speed and the higher range of eccentricity, of course. Moreover, equation 2 and equation 2 can be easily included in any Monte Carlo methods in order to follow the motion of asteroids across the mean motion resonances in the main belt, and it can be very useful because of very expensive, of course, computer time. And our future studies on the direction regarding this problem, regarding this issue, and the direction between the mean motion resonances and the Yarkovsky drift speeds will include two-body mean motion resonances with other planets as well as three-body mean motion resonances. Moreover, in future work, we plan to include asteroids' orbital inclination. That's all. Thank you for your attention.
Thank you, Dr. Milić Žitnik. Any questions, comments? You may ask a question or you may put the question into the chat box. Okay, if there are no questions, we may proceed with our next speaker. This is Dr. Nataša Todorović, also from the Astronomical Observatory of Belgrade, and her talk is Short-Term Chaos in the Solar System.
Okay.
Nataša?
Da, jel se čujemo?
Čujemo se, možeš da počneš.
Ali treba mi opcija da delim, share screen. Ok, čekaj da vidim.
Now you can share your
Share screen. Share. Ok, čemu možda pustim i video.
Stavi u presentation mode.
Ovako. Hello everyone. This is the first online conference for me. So I hope, first of all, thank you for the invitation, and I hope that the next conference will be like in the good old times when we all meet in person. Here we are still in the solar system, which is probably not probably, surely the best studied piece of universe. Here we see a nice collection of photos taken from different objects in the solar system, and each of them could represent another research topic. But the global image could be of the solar system could be observed from 2 points. The history, let's say, history of the solar system, where it's important to understand the formation and evolution and processes, and such studies involve very long timescales that go up to billions of years, and some future perspectives. And some of the main points there could be prediction of asteroid approaches or maybe even impacts, or launching space missions, and there we deal with much shorter times. The basic question and the most important question in celestial mechanics is the stability of the solar system, and the major contributions there were given some centuries ago by Lagrange and Laplace, who first formulated the equation of motion in the Kepler elements, which later led to the secular theory of planetary motion. And there, also Zoran had a speech about this. There we deal with the long-term stability. So in general, in the solar system, we always deal with such stability. But today we know that solar system is not entirely stable, but there are some, let's say, region of stability, and we deal with estimating if they remain stable till the lifetime end of the solar system. And in the few decades ago, two important theorists, Kolmogorov, Arnold Moser, Nehoroshev, gave some approaches and answers in this regard. On the other hand, chaos has some other kinds of questions: how to find chaos in the solar system, how to understand chaos, how to measure chaos. And the pioneer work there was done by Henri Poincaré, who actually showed that there is no general solution of the equations of motion. Zoran also had. Can you hear me?
We can hear you and we can see your presentation. Okay, you may continue.
Okay, I don't know what was the last part, but I actually started with this stability and chaos difference, let's say. So the contribution of Poincaré, except that he proved that the equations of motion do not have a general solution, maybe a little bit less known contribution to understanding of chaos was manifold representation of chaos. So manifolds are not very known and popular in this society, but they are some sort of surfaces in the phase space which have a very complex form, and their mutual intersection leads to chaotic motion. They are mostly studied in the framework of mathematical definition, which I will skip here. Also, the full and more correct name would be normally hyperbolic invariant manifolds, but here I will use just manifolds, or I prefer space manifolds, but invariant manifolds is, let's say, most common. Lyapunov, on the other hand, introduced some numbers which reflect the stability properties of stability, and later such numbers survived in the form of Lyapunov characteristic exponent, and a lot of other chaos indicators were born from Lyapunov exponent, and one of them will be used in this work. So studying solar system always involves long times. And here the motivation for this work was to ask three questions opposite to the traditional questions. What is the shortest time for the appearance of chaos in the solar system? And where in the solar system can we find that short-term chaos? We expect that this is actually the strongest chaos in the solar system, such that appears at a short time, and how this chaos affects the population of small bodies in the solar system. So one first remark would be that we expect that this strong chaos should be related to Jupiter as the main perturber in the solar system. So we will study a region between 3 and 7 astronomical units. Jupiter is at 5.2, so some neighborhood of Jupiter. And we observe the dynamical geography of that region by calculating dynamical maps. We actually run the time and just wait for the first appearance of chaos. So the answer to the first question, I started the fast-Lyapunov indicator, I used the fast-Lyapunov indicator, which is numeric quantity that reflects there is some initial condition, velocity vector, and the logarithm of the norm of the velocity vector, and we track the change in time. So here is how it behaves for 3 orbits. This black one is chaotic. So we see that immediately it shows the presence of chaos. And one important property that we will use for this here is that stronger chaos means faster growth of the fast-Lyapunov indicator, and this was largely used to detect invariant manifolds. In papers by Guzzo, he actually introduced some sort of modified fast-Lyapunov indicator that is more sensitive for the manifolds. This picture shows the change of time in 1,000 years, but we should notice that here at the very beginning, the chaotic orbits immediately, let's say, goes away from the two regular orbits. So we will use this property for our investigation and to answer the two questions that we asked. So we study one portion, as we said, between 3 and 7 astronomical units. The eccentricity range is the whole that covers elliptic orbits between 0 and 1. And in that domain, we take a large number of initial conditions, and for each of them, we calculate the corresponding Fourier. And it is important to say that the initial conditions do not have a mass. The remaining orbital elements are all equal, as well as the initial epoch. We use a well-established software Orbit 9 and a model with planets from Venus to Neptune. And we have to say once again that for such short time, we expect the detection of invariant manifolds. Invariant manifolds are some sort of two-fold objects. By forward time map, we will observe the stable manifolds, and by backward time integration, we will observe the unstable manifolds. So the answer to the first question, what is the shortest time for chaos to appear in the solar system, is one orbital revolution of Jupiter only. So it is 12 years. Extremely short comparing to the other previous studies. And in fact, the more correct answer would be during the first evolution, so even shorter than 12 years. So how does this short time, in fact, this is the backward time up, so minus 12 years. Where in the solar system is that chaos located? We observed this sort of shape, which I can say, according to my knowledge, was not observed before. And first of the white part corresponds to very chaotic particles. And the only thing that we know that should produce strong chaos are the mean motion resonances. And they also have a V shape, but we should first exclude any possibility that this could be some giant unknown resonance or anything like this, because nothing can happen in one orbital revolution, eventually the 1-1 resonance, but this is not at 4.5, and we already know where is it and how it behaves. So what is it? What is the origin of this part? Of course, it is difficult to answer that question, but I would like to make just few remarks that usually in the lower in the part where the lower eccentricities are, we have downstairs are the asteroids and upstairs are the comets. And usually the upper part is more chaotic. But here we observe that the most chaotic part is the lower part, basically with low eccentricities. Also, the calculation time was quite long because I expected that this map appears immediately for 12 years, but it took like some 15 hours in a desktop. So the reason for this is the strong divergence of the white chaotic particles, and it's difficult for the integrator to track such orbits. So before we try to explain the origin of this, of course, we know that it should be Jupiter, probably. We take just two particles here along at the most stable part of this structure and observe how they evolve in time. First, the blue here, the blue circle. Here it's the orbital evolution of this pathway during 500 years. And we see it has some sort of random walk in the semi-major axis eccentricity plane. But and it makes also some sort of V shape, but I overlapped and it does not correspond to this V shape, because this V shape is in only one orbital plane, and this structure, it goes very chaotic along all orbital elements. Here we see the separate orbital elements as a function of time, and we see that the semi-major axis and eccentricity have some sort of jumps. And usually such jumps were observed, produced by close encounters, but none of these jumps is actually a close encounter. The first close encounter happens after 370 years, and this is the moment when the body goes out from the solar system. So it did not even survive the time of 500 years. The second particle here has a completely different evolution. It goes here, first it stays in the local for some while, and this is the enlarged portion of this region, and we see that it makes some sort of a loop and then goes back here, then goes again to the lower semi-major axis, makes another very similar loop, then goes, this should be this line, and then it goes out from the solar system. Again, the first close encounter happened after about 90 years, so it did not even survive for 1 century. So I did a lot of other test particles along this chaotic shape, and there is absolutely no common pattern for them. So something is producing these strong, short-living particles, and what could be the origin of this work? And I have to say that in the long-term integration, in the traditional picture, 500 years for solar system time scales is basically not time. This is an output between two steps in the studies of the long-term dynamics. So I have to also admit that I asked some people, some of them are participating in this meeting, and there was absolutely no idea what could be the strong chaos. So, and this work was done like 3 or 4 years ago, and I left this work because I was not able to give any explanation. And in the meanwhile, I did this exhibition. Here are some of the organizers of the conference and some images. And when this finished, I came back to the manifolds and got 2 collaborators from USA, Aaron Rosengren, who was here in Belgrade in some time, and his student, Di Wu. And after being skeptical for a while, they started a new round of numerical experiments. And the first thing they did was to observe such structures eventually in other softwares, in Rebound, in Mercury, and by integrator written by hand. And all of them confirmed the same structures. Also, we were doing, taking other models with Jupiter only, with the planar model, and step by step going to simpler model of the solar system. And all of them also show the same structures. Some calculations were done also by Victor Radovic and this person from Spain, which I don't know how to pronounce. And they also confirmed some of the wild orbits that we saw, and still without having any idea what could be the origin of that chaos. And here I have to express my gratitude to Christos Eftimiopoulos, who, as soon as he saw such structures, he said that those are the manifolds that emanate from the Lagrange points of Jupiter. And this was something that actually confused me, because how can one single point in the space produce all that amount of chaos? And there are other maps, which I did not show, which produce really strong chaos of this kind. Later in the literature, we see that such manifolds are actually very normal in the space flight dynamics. All spacecraft of NASA use invariant manifolds. They all use Lagrange points for parking, and they push, the invariant manifolds can push naturally the spacecraft, and in this way they save fuel, they save money. And but they mostly use the Sun-Earth Lagrange points or Earth-Moon Lagrange points. And recently there was some mission, Le Petit Grand Tour, that use the invariant manifolds of Jupiter in the system of Jupiter and Jupiter moons. And they made some circles around the satellites very successfully. And the common thing for all such studies is that they use the Cartesian element space. And so no, they absolutely don't deal with Kepler elements. The influence to the natural population now for Bojan. it has been illustrated that the comets Oterma and Gehrels actually follow the invariant manifolds. Before, I have to say that Oterma was a very chaotic comet discovered in 1910, and it experienced a close encounter with Jupiter, came to the inner solar system, spent some time in the 2 to 3 resonance, and then came back to the outer solar system. And this was quite confusing without any explanation how is this possible. And by the end of 90s and the beginning of 2000, a series of papers appeared where Oterma was actually explained to follow the invariant manifolds of Jupiter Lagrange points. Also, Shoemaker-Levy, maybe we remember that it hit Jupiter in 94. Last year, one paper in Monthly Notices appeared, and it was illustrated in a spatial three-body problem that it actually followed the invariant manifolds of Jupiter Lagrange points. So I will try to explain in next few slides how do they work. We start from the basic model of the simplest model of the solar system that approximates the dynamics. This is the restricted three-body problem, a special case of a three-body problem. We take a planar case and circular case, and it explains the motion of a small test particle without mass in a system where two primaries, massive bodies. So the two primaries in this simplest case move around circular orbits around a common center of mass, and they are all coplanar for the initial moment. So there are two very important parameters that rule here in this system. First, it is the mass parameter, the mass ratio between Sun and Jupiter. This is fixed around 10 to minus 3. And the second parameter is the energy of the test particle. Also, it depends how is it positioned with respect to the Lagrange points. So how energy rules here. So here we show the system, 5 cases for 5 different energy values. The particle has some sort of forbidden region for different energy values, which are here colored in gray. Here in the first case, actually this is Sun and Jupiter, and the 5 Lagrange points are maybe too small, but maybe you can, sorry, I forgot to do this. Here we see the highest value of energy, and we see that the particle in this case is allowed to move everywhere in the solar system. Here is the lowest value of energy, and we see that it is trapped here around Jupiter as a satellite of Jupiter, or it moves around Sun without possibility to cross anywhere, or around Sun in the outer solar system. So those cases and this case are not very much studied in the literature. The most studied case is the case between these two cases. Here maybe this region is too open, and in this region, this case, this exit to the outer solar system is closed, so also not much studied. So the case, we zoom in now this region around Jupiter here, and we see that this is the Hill region of Jupiter, and we see that the 2 Lagrange points are some sort of gatekeepers. So they control the entrance into the Hill region. We see here 2 lonely points, but in reality, they are surrounded by an infinite number of orbits, of periodic and quasi-periodic orbits. And there are different classes of such orbits, but here I will show you only one such type of orbits, the so-called Lyapunov orbits. They, for one fixed energy level, we have exactly one Lyapunov orbit around each of the Lagrange points. And this is not all. They have some sort of dynamical extension. They are stretching in the neighboring space like in 4 different directions. And now we finally can arrive to the stable and unstable manifold. We see the extension of the Lyapunov orbits like along the blue, the green tube and the red tube. So here in the green part, this is the stable manifold, and it represents a collection of orbits that asymptotically approach to the Lyapunov orbit. So, and the red is exactly, but in the opposite direction. They depart from the Lyapunov orbit, and in the backward time they approach. So each of the Lyapunov orbit with this some sort of surfaces rules the dynamics in this region. So how Oterma or other comet how is it related to the manifolds? So here in the vicinity of the Lyapunov orbits, they have, as I said, a tube-like shape. So they enter eventually into this tube. They are pushed. Here we see the arrows which are better. They are pushed by the stable manifold close to the Lagrange point. Then they are pushed away along the unstable manifolds. And here actually happens the main part. It has to be lucky enough to hit this green stable manifold of L1. And it could be a very demanding task. Here it is simplified, but in reality it's much more complex to find this so-called heteroclinic connection. And if it passes, then it goes through the Lyapunov orbit around L1 and goes along the unstable manifold in the inner solar system. And this is how Oterma actually passed through the through this gate. It can happen that it does not hit the green manifold, the stable manifold of L around the first Lagrange point, and then it bounces back to the outer solar system, or it stays trapped here, or it may also collide with Jupiter. So all those scenarios are possible. Here we see that the tube-like shapes are actually only one approximation of such manifolds in the vicinity of the Lyapunov orbits. But in reality, they have much more complex shape. This is how they look. I took those pictures from internet and they correspond to the Earth-Moon system. So in general, it is super difficult to compute such manifolds. We see that they are composed like of tiny lines. All those lines are individual trajectories. So there are several methods in the literature that can give you methods how to compute such manifolds, but they are all very, how to say, they are possible only in the very narrow energy range. Increasing the energy just a little bit complicates the calculation, so it makes it too complex to be tractable, and therefore they are calculated only locally. So, but locally means inside the Hill sphere where all the, let's say, important dynamics is going on. So let me see what I did. Okay, here is our map, which should be somehow related to the manifold that we saw. And we see that we are far out from the Hill region. This second shape is the stable manifold. So we actually it is a structure obtained with forward time calculation, where we expect that it should be symmetrical to the first one, but we see actually it's not symmetrical because one branch is missing, and here in this part it looks more that they are complementary. So maybe we could say that this is quasi-symmetric. So still
5 minutes. Okay.
5 minutes.
Yes.
I think I will be fine. Let me see. Okay, I'm in the conclusion. So one conclusion in the literature, the manifolds are studied mostly theoretically by mathematicians in the Cartesian element space, only locally, mostly inside the Hill region. And for one fixed energy level, all the manifolds that we saw, this is actually one energy level and the corresponding manifold. So they cannot extend, actually they can extend the region, the energy step by step, and then have discrete values of the energy. So, and they are, it is possible in a very narrow range of the energy between the energy of L1 and L2. Using such maps to calculate invariant manifolds, we are in the Kepler element space, which is, let's say, communicates better with the solar system dynamics. We are far out from the Hill region, and we are absolutely not limited with energy. We can go any region of the solar system and observe such things. Future work, it should be a lot of future work because we just scratched the surface. First of all, we have to better understand the connection of the invariant manifolds that we observed with those which originate from the Lagrange points and their corresponding periodic orbit. We should extend the domain that we would like to study. Also try to see how does it look in 3 dimensions. Also explain the origin of some main belt comets maybe in the context of the manifolds, because if they really so quickly enter into the solar system, then they do not need millions of years to save their ice on the surface and so on. And I think this was all from me.
Thank you, Dr. Todorovic. Any questions, comments?
No.
May I just say a few words?
Yes, please, Dr. Knežević.
Yeah. Well, I am glad that you have found the solution of this problem, which was really quite complicated. And as you have mentioned, I was the one of the people whom Natasha asked for the explanation. I suggested that possibly the cows can be due only to the close encounters, but it turned out that they are not. That this is not the case. However, I would like just to point out one thing, that clearly people working in celestial mechanics and working in the space dynamics are not having enough interaction. Only such a person who can more or less bridge the gap in between the 2 fields, like Christos Eftimiopoulos, could help you. I'm glad that you have found the solution and a very nice paper. Thank you.
Thank you, Dr. Knežević. Any other questions, comments?